recording. Nice. Okay. Let's see, where's my other? Oh, okay, that's on this page. Neat. So here's the program. It's the FizzBuzz, and which is a program that loops 100 times, and for each third number it loops through, I think it prints fizz, and then every like fifth number it prints buzz. And so this is implemented completely with templates. And in fact, if you look at the main function down here, the entry point, this is all done at compile time. So it's not even doing anything at runtime, which is kind of neat. Except for like the printf stuff. So if we compile this, got I did test this beforehand, and we run it, it just prints out FizzBuzz like immediately. So it all of the information up here is basically like evaluated at compile time, rather than like whenever you run the program, it evaluating there. So if we look at like some of what's going on here, I should probably zoom this in. Oh no, I can't zoom. This is the worst. Oh no. Is it okay? Like the size?
Try maybe Control Plus or something. Should work.
Oh, Control Plus. Nice. Thank you. So we're including a C standard library. And that's why we're using printf rather than cout. And part of that, I think, is because of this nice little formatting stuff. So we'll just start off with these first two templates up here. So these are just structures, right? So if I do this to make it a little easier to read, it's just a structure named fizz. So it's like a class, and it's got an enum in it, and its enum has flags, and it's set to 0. And this template takes in one argument, and it's restricted to integers. So it's only going to take in integers. And then this template. So this is a more specific template. This has more like restrictions and specifies more things. So if anything were to is everybody okay?
Hello?
Hello?
Can you hear me?
Yeah. There's a bunch of people like leaving and joining, and I'm wondering if people are having connection issues.
Oh, okay.
I lost where I was in explaining this, so I'm just gonna like not finish that. Is this the? Yeah, this is all I need. Okay. Who's that over here? I'll start off somewhere else. Might be better anyway. So we're gonna make a util.h file. We should probably make a main.cdv file. So templates are nice for when I should have started here. Templates are nice for when you don't want to repeat your code. That's kind of what they're meant for. I'm gonna include a bunch of things that I probably don't need to include, but they're all included in my original file over here that I wrote earlier, so I don't know how many of these I need. So if let's say we want to make like a data structure, right? For instance, we want to stack. We can start with we could make a stack structure or class off the bat, right? So struct stack, and then give it, maybe have it just wrap std vector, and then we could give it like we have to specify the type here though, right? So we have to know what we're going to be storing in here, which kind of sucks because then we have to rewrite code a bunch. Like we would have to name this integer stack or something like that, and then have like a float stack and like a character stack or something like that. And then if we wanted to do with objects, it would get even harder. So there's this neat thing that's in C and C++, where you can make templates, and you just specify that this is the name of like a type, like an integer or float, or it could be a class type as well. You can actually write class here, and it's functionally the same. I just like type name. And so now this means that you've got this sort of type name variable that you can put in different places in your, I should do that, in different places in your class or structure. And now if I were to call, or if I were to construct a stack, right? I now need to specify a type here, right? So it's like the same as vector. And that's how vector works as well. So you can put a bunch of different types in there. And all you have to do is write the code generically enough that you're not trying to do things with data types that the compiler is going to get mad at you for doing. All of this gets processed before compile time. It's a lot like the precompiled headers and stuff. And then when things need to be like optimized and linked and all of that stuff, that happens after. So there are actually a few uses for templates that actually come out of that behavior that they resolve before compile time. So before I go off on that tangent, if we want to make like member functions methods, right? We can do it, and they would still need to use type, right? So if we wanted to push something to the stack, it would have to be still of the same type. We wouldn't want to specify some different type or have it be different than whatever this is, because then, you know, it wouldn't be able to go in the vector. So we can just put t here again, and we can take in things like we can still specify things as being like a const reference or a pointer or something like that. And it'll still do its implicit conversions and stuff like that dynamically as it comes across the code that we write here. Also, you can use it as a return type, right? And then just I think you sort of get the idea with that. That's kind of all that I had to show that was interesting in that. Just for completion, I'll put all the code in here. I'll probably just copy paste this code into Replit or something later, or I could just shove it in a GitHub repo and link that. It doesn't really matter to me, so if any of you have preference, then just let me know. Another cool thing about this is like there are a lot of things that you can do with basically any type, but it has to be the same type when you do that thing, right? So like a really simple example of why you might want to use a template is for a swap function. So you can have you can have two variables that are of the same type, right? So this t can't change between these two things when, like, it's still within this. It's if it's still using this template's type name, right? So this, it just has to. This just takes in two variables of the same type. Whoops. And there you go. You've got this swap function that you may have had to, like, copy and paste a bunch of times and then change all of these to, like, float for one and then char for another, and it makes your code so much nicer and cleaner. The only problem, though, is, as I'm sure you can imagine, there are a lot of functions where you might not want every data type to be used for it or even be valid for it. Sometimes template errors can be like, your compiler might not give you the most useful information. So we want to kind of avoid errors like we usually like to do. So the next thing I wanted to show you is that you can do you can have a default value for it, right? And so I have this sorry, I lost my place on this. Okay. If you wanted to make like a, oh, I should probably name it like vector3 to distinguish it from the other kind of vector. And okay, yeah, there's a so you can make like some other sort of data structure, but with vectors, I chose a vector because you can also do things like operator overloading. So do t x y z, and then you can have like whoop. What happened? What? Okay. There. What's I doing? Right. And that's useful for vectors, obviously, because when you multiply vectors together, like three-dimensional vectors specifically, when you multiply them, you usually do dot product, right? So that can be really useful for the operator overloading stuff. and you can still just do this time, like now if you want to create an object of type vector 3, you can just do that and it'll automatically just assume that it's going to be float. So that's neat. I need to sort of resize this thing. The next thing I'm gonna show off here is the template instantiation. So you can when you're writing templates, right? You might want different data types to have like different effects in the code there, right? You might not want it all to work exactly the same way, but it's still not like you wouldn't want to like copy and paste all of the code. There's just like some functionality that needs to change. So and the other there's that, and then also you need to template instantiation is something you probably want to do anyway if you're using a whole bunch of templates in your project, because templates need to be instantiated to be compiled. So if you don't instantiate them before you compile, if that template's not used in your project, those templates won't be added to object files. And that means like if you're creating say a math library for this vector structure, right? And you add like a matrix, so and it's really good, and you got it to run really fast, and you're like, hey, internet, I got this thing, and then people want to download it and use it in their stuff. They can't if you don't instantiate your templates. And template instantiation looks like this. Should like that. You can't put it in here. But you can put it in here for some reason. Interesting. Wonder if it just wasn't giving me an error and it shouldn't be doing that. Why is that white? It's weird. Anyway, this is what like explicit type function instantiation looks like, and this is what implicit type would look like. So you would have like you have this type is being explicitly defined to the template, but you can also just pass in something of a certain value, or of a certain data type, I mean, and the compiler will check for you. There. So then you've got template specialization. So when you've got a template already created, right, like that's defined up here, you can add other versions of that template if they do different things with different types, and then only have to define those types rather than the whole thing. I think I already talked about that, but and they resolve in decreasing order of specialization. So when you have like the actual data type there, right? That's fairly specialized. More specialized than this, I believe. If you were to make it a pointer or a reference, then that's even more specialized. And then if you were to add const to it, that's even more specialized. So it's just useful information to know so that you know in what order things get called. So like if you have a const float pointer thing that you pass it to the print function, then this would have been called before anything else was even looked at. Or rather than anything else being looked at. I apologize if I'm hard to understand today. I don't know if I'm just nervous about teaching templates or if I'm like losing my mind. But
Templates do that to you.
yeah. What is this? Oh. So here's something, another decently practical example that I think you guys might appreciate. Oh, and it also gives me a chance to explain something else. So this doesn't have to be T, by the way. This can just be like, I could write my name there. It can be whatever. It functions similarly to variables, but usually you capitalize it so that you don't get it confused with actual variables. Syntax highlighting helps with that, though. You can specify more than one argument in a template. So if I wanted to make a sorted array class, right? I can specify it like this. Why did I do this like this? I made a class and then I just made everything inside of it public. Okay. So an array named R, right, of type T with S as its size, right? Yeah, maybe. I wonder if I forgot something somewhere. If the program just hates me. It's not highlighting this, and that's sketching me out. Anyway, so this size specification here is like the maximum size that the array could be, right? That's why we're creating this array with that size, and it helps to have that at the beginning of, creating the array, because then you don't have to allocate things on the heap. You keep them on the stack. And we're also going to talk about some other neat memory tricks that you can use pointers to, or you can use pointers. I guess pointers are part of it, and templates to do. So like count, and then do I want to, should I add here? I'm actually just going to type all of this out, I think, because I want to explain it as we go. So first thing, if it's going to be a sorted array, we should probably make a sort function, right? Inside of the sort function, we only really want it to sort if there are things in the array. So if count is more than 0, then we'll sort. I think that sounds like a good idea. And I could have been fancy and like looked up a sorting algorithm and then pretended like I knew how to write it. But instead, we're just gonna use standard sort because it's probably better than anything I'm gonna write anyway. I think that's probably a good example.
Bubble sort.
Bubble sort. Yeah, I could have implemented bubble sort. I think he's right. Oof. Wait, that's from my other code. There we go. I named it element count, which is like longer than count, and I think I just did that so it was easier for me to read, but I don't know, I don't feel like typing that all out. So now we're going to kind of shove another template in here. Really creative type name, type 2. Actually, I forgot to put an insert method, didn't I? I forgot to. fingers. Okay. So now back to this guy, the template. Now we're gonna do Did I spell that right, or am I stupid? I think I spelled that right. Okay. Crazy. Oops. So we're gonna make a constructor that can cast this array of whatever type it's created as to the type of a different sorted array, right? And probably put output because people use out for things. What? How are you guys holding up? No. Oh, I'm getting encouragement. I feel bad. May I ask, what is R, the element you want to insert to the way? Yeah. I'm sorry. I should have the side open too. What I'm gonna do, I'm gonna move that over here, and then I'm gonna try and be able to read this code still. Okay. This is gonna encroach a bit. Okay. Why does this look like this? Is this 'cause this isn't on the same? Yeah. No? What's going on in my life? Huh. Here we go. I'm wasting people's time. Sorry. Anyway, so we've got sorted array output, right? And then we have, why'd I make that unsigned? Was it because it was mad at me for having element count? Yeah, okay, that's why. And then so we instantiate output as a sorted array of whatever the type 2 is, right? And we don't give them control over the size because we're just casting, and it's going to be the same array anyway. All right, I remember why I did that. And then we just we do output insert, and this is maybe like I could have probably done things like this better. I could have probably done like, I don't know, like maybe like a pointer or something like that. But then when you're casting, you know, I could use like dynamic cast or static cast, or whichever one of those is the cast that I would need for that. But like this is simple enough, and it works. So, and it cast like a wizard. So void. I'm gonna add a print function to this. But actually, before I do that, I wanna do more operator overloading. Whoops. I should. At some point, I should put together like a large pile of like best practice stuff and then do that in one session so that we can get all of that pain out of the way at once. So it's really kind of like you want to write code that the compiler knows how to optimize, right? So the more specific you are, the less flexible your code could be, but the more easily your compiler is going to be able to optimize it. So you using const when you can, and trying to be explicit about the type of your data, not using auto all the time, things like that, like using const expr is another useful. It just makes the compiler happy. So that sort of thing's kind of good to keep in mind and maybe pay attention to as you're looking at examples of other people's code and they're using constant places and you're like, why don't they need to be able to mutate that data? We're going to use a string stream. You know what? I'm kind of sad because I did this a real neat way. And I have to wait until we do lambdas to show you. Yeah, so just... Yeah, constant just means that you're promising the compiler that the whatever's in there is not really going to change. I should also go over standard library stuff. There's so much that I just didn't think about. I got excited. Sorry about that. Should have probably like gone over string stream by now. String stream, you use these bit shift left operators. You can shove stuff into the string and make it bigger. You can use it like cout. And then you can also just have it return as a string. So that's neat. Yeah, all this does is it just takes each index and then lists it in order. and that's whenever we cast this thing to a string. And then for our void print method, we'll have I think it formats that for me whenever I put in a semicolon anyway. Yeah, I'll just put this is cool. For the print function, all we do is just cast it to a string and then put it into cout. And so we get to use this basically as a print function. What's next? CRTP. Wait. Okay. Now this is neat. So now we're kind of getting to the point where there's some cool stuff that we get to do. Let me look at, talk about all of this stuff. Oh, there are variadics in that. Like parameter stuff. All right. Maybe we'll talk about that next time. You can calculate Fibonacci sequence up to like, I think the 47th term, because that's as high as what, no, up to the 46th term, so that's as high as what can be stored in an integer. So, but that has like parameter packs and stuff like that. So, I'll show you guys that next time because I think the variadic stuff kind of fits in well with lambdas. Okay. So this is neat. Something that can be kind of unfortunate about template classes. Oh no, not about template. About regular classes, is that when you use polymorphism, you kind of have to deal with like dynamic binding, and that can come at a performance cost. With CRTP, which is sort of like a structure you can implement with templates, stands for curiously recurring template pattern. It allows you to do like a static form of polymorphism. So all of it gets resolved so that the compiler doesn't actually have to like say link stuff dynamically here. It can, all the types are kind of taken care of. So start off with the normal template thing. Struct. Just call this base. This is going to be our base class, and we'll have our first function here. Oh, actually, I should wait until I put all of my functions down and make the second class. So we've got a method and then like a normal method and a static method. Remember, I guess my brain doesn't work. So when we make our derived class, we actually don't need, we don't really need a template for it. We could use one, and it starts to, then it starts to look like, oh, I see how this is gonna get complex and awkward. Anyway, so you just do like the normal inheritance thing or whatever, and then make your functions. Oops. Now what's neat about this is that in the base class now, you can call, like, since this is a template and you passed in the type of the derived struct, then you can just do I called it static function in my thing, which would have been easier to read for you guys. So from this base class's function 2, right, we do this call and we don't have to worry about the function being virtual, right? Same thing up here. This takes the whenever you have a derived object in the base class type, and they both got the functions or whatever, now it checks to see, okay, is this, I'm just gonna call this thing and it's gonna cast it to the derived class, and now I'm gonna use the derived class function 1 down here. Oops. I gotta move this so that I can actually read. Okay. What does static cast do? So static cast will cast. Static cast can cast derived classes to base classes, or no, the other way around, I think, or maybe both. I don't know. There are like 3. There's static cast, dynamic cast, and then const cast. Const cast is kind of self-explanatory, but they're meant to like help you be a little bit more flexible than what you can do with just like normal implicit casting, or like, and avoid like having people start just manipulating pointers and then having undefined behavior. So, reinterpret cast. Oh, okay. Yeah, so this is super useful. It's super nice. And I'll actually go to further detail about that in a bit. We're gonna do something that I'm not like super sure is extremely, I guess it's pretty practical. It just makes things kind of look nicer. I don't know. It's but you'll see, I guess. So do I have print in here? And now I've got these prints out here. I'm gonna delete. No, I'm not gonna delete these. I'm gonna put this in its own namespace, just to. I could have just called it something else. So we're making a print object, like a printer, and we're taking in an OStream, an OStream reference, which we'll call pstream. I haven't defined this very well yet, have I? This isn't okay. All right. And this needs to have a. And this needs to have a. And this needs to have a. There's got to be like so many semicolons I'm missing. It just won't highlight. Okay. So we need a stream reference. Okay. Oh, this is why. Okay. Do that. Though I think I might just need to do that. Yeah. Now it's okay. Should figure out what you guys are saying. It's just someone typing. So we got a constructor. Then so we're gonna have this function print return a print reference and have this type, this reference type. It's a reference. And then inside here is to what's happening? So we just shove p in the p stream and then return a pointer to this object. Okay. So I have something wrong somewhere. I need to learn how to not get so caught up in figuring out what is wrong with my code. Sorry. Anyway, now I do we can do, I can make a print object, printer, and then construct it with cout, and then we can do printer dot print hello, and then dot print space dot print world. And we can just end it with a semicolon. You can do this forever because it just returns a reference to itself. Semicolon at the end of the constructor, maybe. I wish I knew. wish I knew. Well, that's okay. But this will work if you write this and it compiles. You can actually, you don't even need to. What? Wait, what? I'm using this namespace and then print. I'm sorry. You don't need to construct this. You can, well, you can do. I guess you are still constructing it. Well, it can't be just C out. It has to be standard library namespace. Wonder what happens if I added something to the standard library namespace in my program. Wonder if they'd yell at me. You can also basically combine the last two things we just did and do the chain, do like this like print chaining polymorphically. Sick. Okay, we made it to the end of that. Oh, we dropped a lot of people. I don't blame anyone. Okay. So you can use templates to enforce certain types in other templates. So if you write something like this, right, template type T, and then give the structure, and I'm naming it precision type, so just something that has stuff after decimal place. And wait, no, it's to the, what? Do I have to put a semicolon at the end of namespaces? I'm so confused. This should be green. And it's C++ too. What? Okay, whatever. Anyway, you can like oops. I need to scroll down in this. I had to put this near the bottom. Why is there so much here? I prepared too much for this. I have too much. Static cast converts one type to a different type. Apply certain rules to it if necessary, and converting from float to an int. Okay. Dynamic casts for class conversions. Okay, so I just used the wrong cast. Const cast and reinterpret cast lets you convert basically anything into anything without any conversion rules. It just takes the memory and interprets it differently. Yeah, I had to do reinterpret cast for like transferring memory in the Vulkan engine. I think I still have the... Okay, where is the thing I'm looking for? Oh, okay. Right. Okay. I might just be blind. Was I blind? Yep. I was not blind. Okay. So we've got this thing, and we want to make a function that only uses floats and doubles, right? So what we do is we template, type name T, and then we do, and now we create a type alias. So type name restrictor, or that's the other code. Precision type. T. Result. And then what was the function that I used? It was a good example. I think I used like smooth step or lerp or something. I don't know. I'm just gonna like yeah. And then whatever happens in here, and then you just return whatever you're gonna return, but so the way this, I forgot an E here, huh? The way this works is I told you about the templates. The more specific instances will get like, they'll resolve rather than like the general case, right? So, people keep leaving. So the when the type that's passed into this precision type is a float or a double, then you type def. If it's a float, you type def float result, and then if it's a double, you type def double result, right? And that just makes a type alias, so results just either double or float depending on what's passed in. If it's neither of those things, it doesn't type def anything, and so then this just doesn't work. And so that's how you include a little bit of safety in your templates. And then oh boy. So the last thing, more and more people leaving. I'll finish this up quickly. The last thing I was gonna show you guys, I was actually like super excited about this, and I think I was working until like the last minute with this thing. Was let's see, is this? Where's the top of this? I think this is the top. Okay. So at this, and I might need to include some stuff, so I'll put some space at the top of the file and see what's included in this other file. It's these things, but I probably just copy pasted them, so whatever, I'll just copy paste them. I mean, there's no errors, right? I can't tell. It's been debating me this whole time. Maybe I should save more often. Maybe that's making it wig out. Maybe it's because I have like 9 million things open on my computer. So this was this is a matrix structure type that you can. It has like, what do you call it? It's got the like addition operator overload or whatever, and you can chain that as many times as you want. So you can do like, if you've got A plus B plus C plus D, right? And then all of that, you can chain that all together. They're all matrices, and then the addition between the matrices is actually really efficient, because instead of copy constructing, it does operations with move, right? And that can be really, really useful when you have a matrix class, because if you're making like a real big matrix that's real big, that's a lot of numbers. And then you want to move them, you don't want to copy them, because then you have to end up moving them more than the amount of times you would have had to move them before, and you have to take up more memory space, and you have to deal with like read and write and access speeds and stuff like that, and there's a whole bunch of things that's like just makes it unnecessary. But if you and it doesn't really get to be a gigantic deal until you're interacting with like a real large amount of data, but like that's a real problem for lots and lots of programmers. Like people making those machine learning libraries, or people writing them game engines, people who just want to do like neat rendering stuff for fun. Like they'll have a laggy GL shader and be a little sad. They thought their scene was neat. Um, so that being said, I think uh, all of the stuff that I just taught you, you should never use. To be completely honest, I'm not a big fan of headers. But I think in the right situations, like they're really good. And I think they're really neat, and I think they reveal a lot about the language, C++ as a language. But I don't recommend using them because they um, they kind of like abstract away specifics that I think are good to have as specific things, and they make your code a lot harder to read a lot of the time, and they're just really like complicated for the compiler too. Like they're um, and it's not as easy to tweak. Like um, if you're really trying to optimize for something that you've got templates in there, then um, sometimes like it's just doing weird things that you don't know what it's doing. You don't even know how it's resolving. You've got to think about like all of the ways that it could resolve. Um, it just it makes things a lot less straightforward. So let's see if there's I'll go through this a little bit and just explain any of the things that I think might be useful to explain. Um, uh, so, well, I'll start with the um, static polymorphism sort of stuff, right? Um, so, REF, this is just getting a reference of the whatever type, right? I could have just made this T. It probably would have made it a little bit easier to read, honestly, because everything starts with mat in this file. Um, but yeah, so these are different than this, and these are basically the derived type. Um, so you cast this pointer to the derived, and then that's the uh, reference. It's returning a reference to whatever object type. And then I've got matrix, and then I've got matrix math. So this is like this object only exists when you're adding, well, currently when you're adding matrices together. And it I don't think it doesn't have any, it doesn't allocate any memory of its own, right? So it takes in references, constant references to um, uh, different types, but so these types are restricted by they can only be this math class or this matrix class. Just by the way that they're used, I believe, but like it's not explicitly set up that way. So this inherits from a matrix object, and then it passes itself. And with the, so if you're, this is what I was saying about templates this is what it looks like when like templates, you can see why this would get confusing, right? Like you just get these things nesting, and there might be a thing where it's like that, right? And then like you've got these templates, and they're referring to other templates, and you have to like look through those and understand, and like chase down kind of with the whatever behavior you're like trying to look for. If there's like a bug or something, there's so many things it could be doing that you're probably not even gonna think about. Also, there's a lot of const. There's a lot of const in here, and there's a lot of references being thrown around because both of those things make things faster in this situation. So I tried to use those things as much as possible. There's I'm also using like initialization, like compiler initialization chain or list or whatever, and same thing with this, right? As much as I can, when it's being created for the first time, I have to create a new, right? This just a set size thing. I think some of the methods that I outlined here aren't actually implemented. They might be, but I don't remember. This overloads operator plus and then so it'll take a matrix object on either side, right? So this is kind of the main thing that gets resolved or gets called, and I'm not doing really well right now. I totally lost my train of thought. This gets called with type 1, this gets called with type 2. So what happens here is it looks for the matrix object type 1 and type 2, right? And for the left-hand side, it's trying to expand like whatever amount of matrix math references that it's getting. And then that way, once it's expanded it all and it's like all nested, then it can finally finish it all up and like add them together. Why am I using matrix pointers? Or what am I using matrix pointers for? Oh, that's what's for. Yeah, okay. So, right. Why did I forget that was a thing? So, we've got constant pointers and constant reference. I think this type's actually defined, but this one's like the template type. It's ridiculous. And it just gives you back pointer. That's what it does. What is? Oh, P is up here. Okay. Not kind of. We're learning about templates. I'm losing my shit and rambling, and everybody else is quiet.
Or are you doing great?
I don't know about that one. Ugh. Okay. We're almost done with this. I just need to finish this last little bit. I'm going to focus on this. This is where the magic happens. We've got an array of matrix pointers. They aren't like their own memory, rather other than them basically being mapped memory locations and VRAM or whatever, but like they're not holding big old numbers and whatever, like doubles or, and they're they are just pointers to the number of matrices, not the number of elements in the matrices. So that's a lot better than the alternative. But we sum up all the matrix was in a nested loop, and then return or we add that all to sum, and then for each thing we just sum up each cell into like its cell. Like all of the 0 zeros get added up, all the 1 ones, and so on and so forth. So and that was probably self-explanatory considering it's a matrix class and it's supposed to be addition. That's basically everything that I had to show you guys. The only other thing, neat thing, was the Fibonacci thing, and like, you guys are super cool. So if you want to look at it, like, I'll compile it, and then well, to go to main, and then not even including fib. Does it print the value anywhere? Ever? This is something that I saw on C++ Weekly, which is really, really dope thing to, if you're like interested in C++ as a language. He talks about some really interesting stuff. He talks about compilers and kind of what goes on in the language when you're using certain features. And it's just kind of an interesting thing to listen to and gain some insight from. Yeah, Jason Turner. No, I don't think this doesn't look like. Yeah, it doesn't look like I'm. Oh. Okay. Right, I remember now. So I've got this thing, and this is where my thing happens. So I just take this and I go into main, and I go down to this, well, this is gonna print out a bunch of different things. Whoops. That was B, not B. And let's double check. Say impl implements this, and then so it's like an index sequence and an array, and there's these dots, which means that there's a variable amount of arguments. So we'll talk more about that. And we do lambdas. This is main. Okay. Oh, I could just be print chaining this thing. Let's go. I'm gonna say 46, and we're gonna int q. Never use that. And then does alt work on this? Yeah, I like IDEs that allow me to use alt. I shouldn't print this more than once. So hopefully, if everything went well, I can just whoops, and then up here and do slash there. Okey-dokey. Okay. And that then this one, it's not capital. I don't know if that, I don't think that matters. And we'll say Fizzbos. You see, what? Oh, right. I'm in a different folder. Oh. Ah. Oh, I didn't save. Smart. Good job. That fix it? No? Okay. Yes? Maybe? No return statement function returning non-void return type here.
It's
219.
just Wagnings.
What?
It's just Wagnings.
Okay.
Doesn't matter.
Neat. I couldn't read the most bolded word on the screen. Okay. Well, there's your number. There's your Fibonacci number, guys. We did it. We calculated it with when and the I'm upset because this was gonna be where like I kind of ended off and be like, look, you don't have to use templates. You can just use Nay's formula because it's like a closed formula, so you don't. It's just like linear time, I think. Maybe. But it's not like
If you
whatever
use the
this is.
formula, it should be constant time.
Oh, there's powers. Yeah, I think it's constant time. Oh, the maybe it's the no. I was just speaking like a fool. There was nothing that I was thinking about that was the thing. Okay. Well, I'm glad I could provide you guys with such a wonderfully entertaining and flawless, insightful um, instruction today. It's very. I'm sure you guys learned everything you wanted to know.
Yeah, I learned stuff.
This is
Learning
why.
C++ languages. You did great.
This is why I want you guys like I always want to make sure you guys know like I'm around during the week on like during time. So if you have a question, you can DM me. It's I'm open to that. And during class, if I'm not making any sense, like actually talk over me, because I want to get some feedback at some point. Some I don't know. This felt like a big mess.
Well, I just joined, so I wouldn't know.
You didn't miss anything important. Don't worry about it. I mean, I wouldn't. I just told them like 10 minutes ago. I don't recommend using most of the stuff that I just like presented. So
Yeah, templates. Yeah,
templates,
I mean, yeah.
but like they're useful sometimes.
Yeah.
Man, I was actually a little bit confident before starting this, and
Have
then
you gone through like the C++ standard library?
I mentioned that at the beginning that I feel like I kind of left some of that out, most of that out. Like, yeah, I didn't talk
Right,
much
yeah,
about
I mean,
that,
there's
unfortunately.
documentation about it anyway, so.
Yeah, though, like my goal was to kind of, I guess my goal was to teach the language, but then it slowly morphed into, um, show language features as I understand them, or like the broader kind of strokes of the language in my eyes.
Okay.
And I don't know uh, if that's a good or bad thing, because it feels it's like sort of unstructured and like um, back and forth and maybe hard to follow. But I don't know. Nobody's told me to stop doing what I'm doing yet.
There you go, that's the good side.
Yeah. So once that happens, then I'll know.
Well, what's your favorite language feature
What's my favorite language feature?
for C++?
Malloc.
Templates.
But
Malloc?
that's like C. So
Malloc.
Are you serious?
I mean, that's why I
Like
use
C-style Malloc.
like that's why I use C++ to like do shit that I can't in a language that's easier to write in than C++, you know. I mean,
Yeah, fair enough. I think I like
Yeah. Why not
operator
you?
overloading.
yeah, like
So,
operator
you
overloading.
make code like really hard to read.
Yeah, I mean, I'm always fascinated by like the IOCCC stuff, or, um, but and I also like that operator overloading is to some extent it's a lot more powerful in this language than in others. Um,
Mm.
Why Malloc and not you?
just
I feel like new is so much easier.
the
Because
first,
the thing with Malloc is it doesn't initialize the memory. And that's problematic
Sometimes you need
in C++.
malloc.
because I'm doing like graphics programming, and a lot of it's like meant
Yeah,
to be used with
definitely.
map, like meant to be mapped and stuff like that. Then you've got to flush the memory and like
Yeah, you gotta do it
it's
fast.
weird shit. It's not something I want to talk about, because not only am I not good speaking, but also I don't really know that shit all that well yet. So I don't want to get confident and then say things that are wrong, and then people have incorrect understanding. Because I do that sometimes.